Welcome back, everyone. In this video, I will review a Mozilla article called A Cartoon Intro to Array Buffers and Shared Array Buffers, published by Lin Clark. I will go through this documentation line by line. This is the first time I'm reading it through. So whoever is listening will be learning as I go through it. If you have any comments, please feel free to post it to the comment section. The link to this article itself is in the description, so feel free to look at the description, and you should be able to open this article yourself. So in this article, in the last article, I have a video about that also. In the last article, Lin explained how memory managed languages like JavaScript work with memory. So memory managed language is nothing but the memory is automatically managed for you. In JavaScript, it's managed by the JavaScript engine. And she also explained how manual memory management works in languages like C. I won't go through it. If you'd like, you can look at my previous video to see it. So knowledge about automatic memory management and manual memory management is needed to understand array buffers and shared array buffers. And that's the reason why this article was written. It's because array buffers give you a way to handle some of your data manually, even though you're working in JavaScript, which has automatic memory management. So array buffers give us a way to handle some of the data manually, even though we are using JavaScript, which has automatic memory management. So array buffers provide you a way to access memory directly. So in the next few paragraphs, it talks about why is something like this needed? Why do you want to get to the data directly from JavaScript? So there is a trade-off, as it was discussed in the last article. There is a trade-off with automatic memory management, mainly performance. It is easier. Automatic memory management is easier for the developer, but it has some overhead. Typically, not only performance, but it allocates way more memory, because when you declare a variable in JavaScript, it doesn't know what type of variable. So it will typically allocate anywhere between 2 to 5 times, if I remember correctly. So that's the reason there are trade-offs. And automatic memory management comes with a lot of drawbacks. So in some cases, this overhead can lead to performance problems. We know that. So you would use, I think this cartoon clearly shows when you would use JavaScript, when you would let JavaScript handle it. So it looks like if your application, you don't need, if performance is not a primary criteria, and the ease of use is what is needed, then you can go with automatic memory management. You don't have to use array buffers. You can let the JavaScript engine handle it, is what they're saying here. So it's talking about some of that stuff. So if you create a variable in JavaScript, the JavaScript engine doesn't know what kind of variable, what is the data type of the variable. So what ends up happening is it will reserve like way more space than what you might end up needing to store a particular variable. The memory slot might end up using 2 to 8 times larger space. So that is a lot of wasted space. But JavaScript engines do it just because they don't know what kind of data type you'll be storing. So on top of it, certain patterns of creating and using JavaScript objects make garbage collection more difficult. So if you're using manual memory management like in C, you can dictate when to allocate and when to deallocate memory. So there is no wasted space if you manage memory, obviously. So in the next paragraph, so most of the time, it's not worth doing memory management manually for most use cases. The use cases that require manual memory management are use cases where performance is really important. And the footprint of the application is also really important. You don't want to use up, if you don't want to use up more space than what is needed, then you would use it. And also if performance is really important, then you would use it. In most cases, the gist of it is in most cases, they're saying you won't need it. So if you need access to the low-level data in a fast way, so basically wherever performance is important, then in those cases, we would use ArrayBuffers and SharedBuffers. So the cartoon clearly shows that. So if you see, they have a React app, and the React app, I think it's a WebAssembly React app that is directly accessing memory. So we would do that where performance is really important. And as you can see, if you need more control, then more control for performance fine-tuning, they're saying that use ArrayBuffers and SharedBuffers. So to summarize this section, in this section, they say you don't have to, for most use cases, you don't need to use you don't need to manage memory manually. But wherever performance is a criteria, in those places, performance, not only performance, but the footprint of your application should be as small as possible. In those cases, you would use something like you would manually manage memory, and you would use features like ArrayBuffer and SharedArrayBuffer. So in the next section, they talk about how does an array buffer work. It basically works like a JavaScript array. The only difference is in JavaScript arrays, you can store object strings. You can store a lot of JavaScript data types. You can put any JavaScript data type. But in a array buffer, you can only put bytes. You can only put things that are bytes into it, is what they're saying. And they show an example for a regular array. If you see on the left side, a regular JavaScript array takes, looks like a number is the first argument, object is the second one, third one is a string. But in an array buffer, if you see, the only thing you can push is anything of type byte. So you can put bytes into it. That's all you can store in an array buffer. So one thing I should make clear is that you aren't actually adding this byte directly to the array buffer. So the array buffer itself doesn't know how big the byte should be, or how different kinds of numbers should be converted to bytes. So the array buffer looks like it's a bunch of zeros and ones all in one line. It's like a continuous set of binary values. The array buffer doesn't know where the division should be between the first element and the second element. The array buffer doesn't know how big your first element is or how big your second element is. So to provide context, to actually break it into boxes, so we need to wrap it into a view. So you need to say, hey, array buffer, you need to map it into a view. So we'll see how they're done. So the views on the data can be added with typed arrays. And there are lots of different kinds of typed arrays they can work with. Basically, the views on the data can be added with typed arrays. The typed arrays obviously have a fixed size, each one. So they kind of define the boundary between element 1, element 2, element 3, like that. Or they give an example. For example, you could have an int8 typed array which would break this up into 8 bytes. Okay, so if your array buffer is a int8 typed array, then at the boundary, each slot is 8 bits. So if you have a 8-bit, if int8 is nothing but a 8-bit byte, so it will break it down into at 8 bits, 8-bit boundary. So if I say, hey, give me the first element, I would get the byte that's in the first 8 bits of the array buffer. Or you could have an unsigned int 16. So if you want to create a different view, so you can say, hey, my typed array is of type unsigned int 16 array. I think maybe we should use this int 16 array. Then it'll break it at the 16-bit mark. So looks like we can have multiple views on the same base buffer. So if you have an array buffer, we can say, hey, it's of type unsigned int, or we can say it's of type int8. So if it's int8, obviously it will break it into 8-bit chunks. If it is unsigned int of 16 bits, then it will break it at 16 bits. For example, if we get element 0 and 1 from int8 view on this array buffer, it will give us different values for element 0 in the uint view, even though they contain exactly the same bits. Yep, obviously, I think, yeah. So int8 is going to split it at the 8-bit mark. You can see this 110, 111, 01101. But so if you see that one, the first element is -19, and the second one is 100 for a int8 array type. But if the typed array is of type uint16 array, as you can see, the first element turns out to be 25,837. So these are different views into the same array buffer. So in this way, the array buffer basically acts like raw memory. So the array buffer in this way acts like raw memory. It emulates the kind of direct memory access that you would have in a language like C. So it kind of emulates direct memory access like the stuff that you have in C. So you may be wondering, why don't we just give programmers direct access to memory instead of layer of abstraction? Giving direct access to memory would open up security holes. So it looks like in the next article. So the question is, instead of emulating access to raw memory, we really don't have access. This is still going through the JavaScript engine. So the question is, why not give direct access to the memory? Looks like giving direct access to the memory would open up a lot of security holes, and it will be covered in the next article. So to summarize the array buffer at a high level is like a typical JavaScript array, but it can only store types that are bytes. So it looks like there are a bunch of predefined types like int8 array and uint16 array. So it can store byte information. Array buffer itself doesn't know what the boundaries are between the different elements. It's like a one continuous data, binary data. So you can provide views into this binary data by saying that, hey, this array buffer is of type int8. And if you say that, then it'll break it at the 8-bit boundary. If you say something like uint 16, then it will break it at the 16-bit boundary. And you can have multiple views. Obviously, each view will have a different value as the first element, because it will be breaking it at a different point in the array. So the question is, why not give access? Why do we have to do this emulation? Why not give direct access to raw memory? Looks like there are security holes that would be opened up. So that's the reason why JavaScript doesn't give you access to the raw memory. So we'll have to go through this ArrayBuffer and SharedArrayBuffer. That's the summary of ArrayBuffer. So now we'll find out what is SharedArrayBuffer. How is this different? So to explain SharedArrayBuffers, I need to explain a little bit about running code in parallel and JavaScript. Okay. So you would run code in parallel to make your code run faster, or to make it respond faster to user events. Yeah, a lot of machines have multiple cores nowadays. So you could run your code in parallel so that it will run faster. So that's one reason why it's used. Shared array buffers are used. To do this, you need to split up the work. So if you want to run code parallelly, then you have to split up the work. In a typical app, the work is all taken care of by a single individual, the main thread. I've talked about this before. The main thread is like a full stack developer. It's in charge of JavaScript, the DOM, and layout. So in a typical app, the work is all taken care of by a single individual, the main thread. So in typical web apps, there is a single thread that takes care of all the work. Anything you can do to remove work from the main thread's workload helps. So if you move work out of the main thread, it always helps. And under certain circumstances, array buffers can reduce the amount of work that the main thread has to do. Okay. Looks like array buffers help reduce the amount of work the main thread has to do. We'll see use cases about that, I guess. So here, I think they're showing a single main thread processing everything in a single thread. But there are times when reducing the main thread's workload isn't enough. Sometimes you need to bring in reinforcements. You need to split up the work. In most programming languages, the way you usually split up the work is by using something called a thread. This is basically having multiple people working on a project. If you have tasks that are pretty independent of each other, you can give them to different threads. Then both of these threads can be working on their separate tasks at the same time. So to summarize, so reducing the work on the main thread is not enough. Sometimes you need to bring reinforcement. That means they're saying we need to split up the work itself. So in most programming languages, you split up the work by spawning off threads and saying that, hey, thread, run this, and let me know when you're done. So if you have tasks that are pretty independent of each other, typically they're given to different threads. So then all these multiple threads can do the work on their separate task at the same time. So in JavaScript, the way you do this is using something called web worker. So web worker is pretty new, at least to me. I haven't used web workers yet. So these web workers are slightly different than the threads you use in other languages. By default, they don't share memory. Okay. a web worker. So unlike threads, I think where web workers are a little different, that they don't share memory. So they're showing a representation of web workers. Basically, there is one web worker here that uses its own memory, and there is another one that's using its own memory. So this means if you want to share some data with the other thread, you have to copy it over. This is done with the function post message. Okay. Post message takes whatever object you put into it, serializes it, sends it over to the other web worker, where it's deserialized and put in memory. So the way you can communicate between two web workers is using a method called post message. You send post message, takes whatever object you put into it, and then it serializes it and sends it over to the other web worker. The other web worker takes this serialized object and then deserializes it, and then it puts it into its own memory. That's a pretty slow process. For some kinds of data, like array buffers, you can do what is called transferring memory. That means moving that specific block of memory over so that the other web worker has access to it. So in array buffers, they're saying you can do it with something called transferring memory. So this means moving a specific block of memory over to the other web worker so it has access to it. So basically, you don't have to go through the pain of serializing it, deserializing it, and storing it memory. So you just transfer the address, I'm guessing, the address of the array buffer, and then the other web worker can use it. For some kinds of data like array buffers, you can do what is called transferring memory. That means moving that specific block of memory over so that the other web worker has access to it. So for some kinds of data, like array buffers, you can do that. You can do what is called transferring memory, as we just talked about it. So that the other web worker has access to it. But then the first web worker doesn't have access to it anymore. So if you share a chunk of memory with the other web worker, looks like the web worker that transferred it over to the other web worker doesn't have access to it anymore. They're showing it in this cartoon. So it looks like this on the left side web worker said, hey, please use this chunk of memory, chunk of memory from my array buffer. So then the second web worker on the right side using it. When it's using it, then the first web worker can't use it anymore. That works for some use cases, but for many use cases where you want to have this kind of high performance parallelism, what you really need is to have shared memory. This is what shared array buffers give you. Okay. So in some use cases, it's okay for the transferred memory from, let's say you have web worker 1 and web worker 2. If web worker 1 is saying that, hey, this chunk of memory, I will transfer it over to web worker 2, web worker 1 loses it. In some use cases, they're saying that's fine. But in a lot of web cases, you want both the web workers to have access to that slice of memory. In those cases, shared web workers can be used wherever you need high performance parallelism. So they give an example. There are two, the left side web worker and the right side web worker. Both of them have access to the same shared array buffer. With the shared array buffer, both web workers, both threads can be writing data and reading data from the same chunk of memory. So both with shared array buffer, both the web workers can be reading and writing data from that same chunk of memory. This means they don't have the communication overhead and delays that you would have with post message. Okay, post message, as we talked about earlier, it has to serialize, then on the other side it has to deserialize, and then store it in memory. So there is a lot of overhead. So with a shared array buffer, it doesn't have that overhead. Both web workers have immediate access to the data. There is some, so the downside is, so there is some danger in having this immediate access for both threads at the same time though. It can cause what are called race conditions. So the race condition is explained in the next article, but I mean, a typical race condition is nothing but, hey, both of them are trying to read and write at the same time. So they might end up overwriting each other's data. In some use cases, that's not a desired outcome. Anyway, to summarize this section, let me go to the top and I'll just do a quick summary. So they're saying, hey, why do we need shared buffer? Looks like if you use a simple, so if you want to communicate, I think is the communication part of it done somewhere else. Okay. So if you want to communicate between, also they talk about web workers, I guess. So in JavaScript, everything is done on the main thread. So in a lot of use cases, you don't want the you don't want the main thread to become the bottleneck. So JavaScript provides what is called web workers that let you create, that let you multitask, that make applications look like they're running in parallel. So in a lot of use cases, you want to, let's say you have two independent tasks. One is saying, hey, add 1 + 2, and the other one is saying, get data from S3. So if you have two different tasks like that, you could have two different, you don't need the main thread to be blocked, processing one and then the next. So you could fire off two different threads because these are two independent pieces of work. So you should be able to fire off two different threads to get the work done. In languages like C and a lot of languages, Java, C, they have the concept of threads that do it. In JavaScript, you have what is called the web worker. Using a web worker, you can do two independent tasks. So this will obviously improve the performance. So they're showing the web workers. The only problem is the web workers can only access, a typical web worker can only access its own set of memory. It can only access its own memory. So if it can only access its own memory, the way you would share something between the web workers is using something like post message. You would send a message. Let's say you want to share an object with from web worker 1 to worker 2, then you would post a message and say that, hey, this is the object I want to share. And web worker 1 will, the platform will serialize it and send it over. And web worker 2 has to deserialize it and then store it in memory and then use it. It's a pretty slow process. So one way to do it is one way to get around this problem is using array buffers. And using array buffers, you can say, hey, this chunk of memory, I would like to share this chunk of memory between web worker 1 and web worker 2. The only downside is whatever you want to share will not be used by whoever is sharing it. In this case, if web worker 1 is sharing it, then it can't use that chunk of memory anymore. So in most use cases, that might be okay, but in a lot of use cases, you would want both the web workers to share the same memory location. Both of them should have read and write access. In those cases, you would use a shared array buffer instead of a normal array buffer. And the downside of this is if both of them are trying to read and write at the same time, in some use cases, one might override the other, and it will cause undesirable consequences. There could be a race condition. So the race condition is explained in the next article. I will go to the last section of this article. In the next article, it's talking about what's the current status of shared array buffers. Shared array buffers will be in all of the major browsers soon. Okay, so looks like shared array buffers are not in all of the major browsers. So okay, let's see. They've already shipped in Safari. Okay, Safari already supports shared array buffers. Both Firefox and Chrome will be shipping them in their July-August releases. And Edge plans to ship them in their fall Windows update. Okay. So all 4 major browser vendors are shipping support for shared array buffers. Even once they're available in all major browsers, we don't expect application developers to be using them directly. In fact, we recommend against it. You should be using the highest level of abstraction available to you. So they're saying even if they're available in all major vendors, they're saying don't use it. Or at least Lin is saying she recommends against it. You should use the highest level of abstraction available to you. Okay, whatever that means. What we do expect is that JavaScript library developers will create libraries that will give you easier and safer ways to work with shared array buffers. Okay, that's what they're talking about. They're saying, hey, if you use shared array buffers, if you want to use shared array buffers, use a library. So that'll make it easier for you to use it. In addition, once shared array buffers are built into the platform, WebAssembly can use them to implement support for threads. Okay. So the other reason why they don't recommend using the low-level API is once they are built into the platform, WebAssembly can use them to implement support for threads. In WebAssembly, you can write WebAssembly code in C language also. So once that's in place, you'd be able to use the concurrency abstractions of a language like Rust, which has fearless concurrency as one of its main goals. So you use a language, once they're built in, we could use a language like Rust, which is by default support concurrency. And we can use concurrency fearlessly. So we don't have to worry about race conditions. So they're asking us to wait and then use something like WebAssembly. I wonder if, so let me see the browser support again. Okay, so I wonder if Firefox and Chrome are supporting this shared array buffers in their, so let me see. Shared array buffers, Chrome, Atomics, and Futex. Okay, so let's see, when is Chrome supporting it? Shared array buffers, Atomics. So in Firefox, it's in development. Edge, it's in development. Safari, it's shipped. Status in Chrome. Oh, it's in development. Okay. Anyway, if I go back here, there is a MDN article about it also. Not to digress, but let me close that. So what's the current status of shared array buffers? Okay, so looks like right now Safari supports it. The other browsers will be supporting it by the end of the year. And the recommendation is not to use it directly. Use a library that makes it easier for you to use it, or use a language like Rust, which will which will handle the concurrency for you. So race conditions won't be a problem. So in the next article, okay, there are tools like atomics that these library authors would use to build up these abstractions while avoiding race conditions. Okay. So in the next article, they talk about tools like atomics to avoid race conditions. So we'll see what that is about. What you should be working with. Okay. JavaScript libraries, WebAssembly threading. Okay. So they're talking about using one layer above the shared array buffer and atomics. Don't use the lower level APIs. Use a JavaScript library or WebAssembly threading to do your work, is what they're saying here. What is servo? The parallel browser engine? One more browser. Anyway, so it's a browser engine, I guess. So to summarize this section, I think support for shared buffer right now, shared array buffer is currently only supported by Safari. The support for other browsers is coming. And the recommendation is use a library or use WebAssembly threading instead of directly using the APIs exposed by shared array buffer or atomics. So let's see what the next article is about. Oh. So in the next video, I'll cover avoiding race conditions in shared array buffers with atomics. I'll stop this video for now.